Okay, so let me continue. So
if you want to go back,
you've seen the talk in the morning when I was a graduate student at Harvard. We worked on a robot called the Robot, based similarly and flat similarly to bees in nature. So if you look at the timeline of this project, you can see a very interesting trend. People start with showing function that large traditional aerial robot can do, such as takeoff or hovering, and then transitioning to interesting functions that are challenging, if not impossible, for larger scale robots, such as swimming, perching on compliant leaf, or impossibly transition from water back into air. So one key theme of microrobotic research is leveraging interesting physics at a centimeter scale to enable interesting functions that are difficult, if not impossible, for larger scale robots. Now I want to address several questions together. First one is, why do we study microrobots? To me, there are two answers. The first one is, by using microscale robot, we can implement new functions. In this case, the same robot uses the same set of wings and actuators to both fly and swim. Okay. More than that, now you can also use microscale robot as a platform to investigate interesting physics at the centimeter scale. In this case, by looking at the flow field induced by a flapping wing robot, we can infer about how a flying insect can generate lift and drag forces. The second question is, what makes microrobot unique? And the short answer is that at this scale, inertia becomes much less important and surface effect become a lot more important. As a consequence, new property arise. For example, you can drop a robot from very high above and see very small change to its performance. And what my colleague has been able to show is that microscale robot can jump off the surface of water. Again, very challenging, if not impossible, for larger scale robots. The next question you may ask is, well, what are the potential applications of microscale robots? In the short term, I would argue there's a lot already. For example, you can think about putting a small camera on board of a legged robot and have this robot to climb inside of a turbine engine and look for cracks on inside the engine. On the longer term, right, we can think about deploying a swarm of microscale robots in very complicated scenarios and through search and rescue mission. Now, of course, this is a very far-fetched vision. We're probably 20, 30 years away from this, but I'll come back to the main challenges toward the end. So what I want to focus on today is very quickly talk about the first two examples, which is complex micro robot that can perform a lot of tasks in multiple environments. And then spending most of my time focusing on the third project, which is something that I've been pushing on at MIT, creating soft actuated aerial robots. So first, let me explain to you what are multimodal microscale robots. Just a very quick background. Flapping wing robot, especially flapping wing robot at the insect scale, has two degrees of freedom. Think my arm as the robot wing. The wing stroke motion is usually actively controlled, whereas the wing pitch motion is passive. Okay. In our lab, we have the capability of doing thousands of those tests, measuring the instantaneous flow field, and then also constructing computational fluid dynamic simulation, so we can understand the underlying flapping wing physics. And by using that simulation, we can reveal about interesting physical questions that typical people in the quadrature community don't think about. For example, we were thinking about what is the similarity between flapping in water versus flapping in air. And if there is similarity, what new functions can be achieved? So we created a challenge for ourselves in that we want to create a robot that is both able to fly in air, swim in water, and make transitions from air to water and from water back into air. So very quickly going over the robot design, we added new apparatus for maintaining stability on the water surface. And we also added apparatus for doing an impulsive jump out of the water surface. So now let me show you a video. So in this video, you see that the robot swims to the air-water interface. And once it reaches the air-water interface, what it does is that a pair of parallel plates then split water into a combination of hydrogen and oxygen. We capture that gas and slowly pushes the robot wings out of the water surface. Once the robot wings are out of the water surface, right, that's using the small apple for small buoyancy, we are ready to ignite the combination of gases and use a combustion to push the robot out of the water. So the next video is going to be quick, so I recommend you to pay close attention to the next video. Okay. So this combustion accomplished within 1/1000th of a second. It's extremely quick. In very large force being able to break the water surface tension, and that allows the robot to transition from water back into air. So in summary, we have created a 0.2 gram robot that is capable of flying, swimming, impulsively transition from water to air, overcoming the very large surface tension forces and passive land on ground. So this is one example of how a tiny micro robot can leverage interesting physics to implement multiple functions. Now, following the same thread of thought, I want to introduce a second robot, which is a lighted robot. In the previous example, we talked about a microscale robot that has to use combustion to overcome a surface tension effect that's 10 times the robot weight. On the other end of the spectrum, if you think about human beings, we barely feel surface tension at all because our weight is more than 1,000 times of surface tension. If we can create a robot somewhere in between, namely if the mass and the surface tension balances, then by modulating the surface tension, we can introduce something very interesting. So again, we start with a physics question. How do we control the magnitude of surface tension forces? And if we can control surface tension forces, what new functions can we achieve? In this case, we want the same robot to be able to walk on land, on the surface of water, transition into water, and controllably transition back on land. Okay, so again, putting everything together, we overcome all the challenges, put together a robot that can start on land, walk on the surface of water. And in this case, you'll swim to a targeted site. I recommend you to focus on the side view of this video. Okay, so once the robot swims to this targeted site, it will controllably sink into water. Okay, so now it's fully submerged, and then it will climb this incline to return back onto land. Again, this process requires very fine tuning and control of surface tension forces. Something, again, very challenging, if not impossible, for larger scale robots. Okay. So until very recently, we continue to push on the functionality of lighted robots. One thing that we are trying to do is to teach the robot to be able to climb on inverted and inclined surfaces, also through surface tension. An idea is that we put a compliant pad here on the belly of the robot, and we put a very thin water film here, and using the thin water film to modulate the ratio between surface tension forces or normal forces and friction forces. So this turns out to be a very effective way for microscale robot to climb on inverted surfaces. Very simple to implement, and in terms of the climbing speed, is 4 times faster than the existing state of art. Okay, so those are examples of how we can leverage interesting physics to enable new functions in microscope. Now, what I want to focus in the next 10 or 15 minutes is shifting gear to talk about a new project that we have been focusing on in MIT, which is creating aerial robot powered by soft actuators. I want to take a step back by saying that our longer term goal is creating a swarm of ubiquitous and multifunctional micro robot that can perform in realistic environments. Okay. So far, what I have shown you today is microscale robots that are very efficient and very capable, but they only work in a single unit, right? My colleague and my advisors are still working on very fundamental problems in microrobotic research, in that we are thinking about new sensing and control mechanisms. We are also thinking about new ways of putting batteries on board of those small scale robots. What we are trying to focus on in MIT was how do we make a lot of them cheaply, and also recently rigid powered micro robots tend to be a little bit fragile. When they run into things, they're not as robust as insects in nature. We want micro robots to be able to robustly interact with the environment, just like insects in nature. So for that, we look into a different field, which is soft robotics. For a very long time, people know how to make soft robots very efficiently, and they're very robust. They have large range of motion. They have different sensing and control methodologies. Starting from the recent years, more and more we see a closed loop control of soft robots as well. In terms of power sources, we can have pneumatic sources, chemical sources, or batteries. But soft robot faces very extreme challenges as well. Most of them are very slow, and most of them are not as accurate. As a consequence, the functionality of soft robots are not very competitive compared to rigid scale. What we really want to do is to merge those two fields and create a new direction of what we call hybrid soft rigid microscale robots. And the idea is that we envision future microscale robot will be powered by power-dense soft actuators, where they still have rigid appendages so they can interact with the environment effectively. And in recent work, we created a soft actuated microscale robot. What I want to convince you is that the robot can operate at a high frequency, has a large strain, very robust, and more than that, because it is soft, much easier to make. And there's emerging properties such as collision sensing, collision resilience, and also by redesigning the robot, we can achieve passive stable flight and also control hovering flight. Very quickly, the robot design is similar to the robot. Only where the main difference is the rigid actuator is replaced by a soft artificial muscle. Okay, so if you compare the soft artificial muscle with a piezoelectric actuator, the bandwidth of the actuator is slightly lower, but still on the order of 500 Hz, but only has a much larger strain. Being able to have a 12% strain really means it's tolerant to assembly error, and that's how we can make a lot of them very effective. And next, to make sure that self-actuated robot can fly, we need to satisfy certain requirements. Don't worry about the exact formula, but let's just remember what the criteria is. First, the lift force has to exceed the robot weight. Next, the actuator force has to balance the robot drag. And finally, we have to match the resonance of the actuator with the resonance of the wings. Okay. And if you look at those three formulas, there are three key parameters being highlighted here, which is the bandwidth of the actuator, free displacement of the actuator, and block force. If the actuator can satisfy those properties, then we say they're flyable. So let's now characterize those properties. We have done a lot of detailed characterization of the electrical model of a soft actuator. We model those as a series RC circuit. And by measuring those parameters experimentally, we realized the electrical resonance is about 5 kilohertz. So the resonant frequency of the actuator is limited by the mechanical shape and material viscoelasticity. Turns out that by designing and choosing materials, we can get a resonant frequency on the order of 500 Hz. So that's the first characteristic. Second characteristic being the block force. You can place a actuator under a nano 17 force sensor. And in this case, we measure the 0 to peak force under a combination of driving voltages and amplitude and frequencies. And you will see that for a 0.1 gram actuator, the maximum force is on the order of 0.2 Newton. The third characteristic is the free motion. We put an actuator under a laser vibrometer and we measure the peak-to-peak motion. Again, at a combination of different driving voltage and frequencies, you will see this resembles a second order system, and you have a resonance peak on the order of 500 Hz. Sorry, I can't show the axes here. Okay, so with those three characteristics, now we can put everything together and infer about the energy density of the system and the power density of the actuator. Turns out through our modeling, the robot is flyable if the actuator power density is larger than 200 watt per kilogram. Turns out that in our first iteration, we have about 600 watt per kilogram, well above the flight threshold. So we put something together. This is the first sort of static characterization video. In this one, you can see this actuator squeezes and elongates. It actually drives the robot at 300 Hz. We're very excited about this result, and we try to demonstrate a takeoff video. And that's again taken probably 3 years ago. It was the first demonstration of a soft actuated robot being able to take off. You can see this soft actuator really looks like a muscle. Okay, but it's very interesting to material scientists, not so much to roboticists. This robot lives over within 0.1 seconds, so in some sense, not very useful. So how do we stabilize this robot, right? Again, for those of you who can't see this movie very clearly, here's a composite image showing the same flight, flips over within 0.1 seconds, not very useful. So to stabilize the robot, we put two units together, and we use a phenomenon called precession. The idea is that if I yaw very quickly, then effectively the robot will behave like a spinning top. And then you write out the equation of motion. It turns out that it's a battle between the moment of inertial tensor and the yaw torque. Again, it's all going to the mathematics. Let me show that in both simulation and experiments, we are able to show the robot can passively fly upward without any sensing and feedback. And that's extremely important for microscale robot because sensing and feedback is very difficult. Okay, so this is an experiment, this is a simulation, no position sensing, no control feedback, just open loop flight. And that to us is very exciting. But more than that, now we have achieved passively stable ascending flight. The core question is, are soft robots controllable? So again, skipping over the design of controllers, let me just say that it is controllable. And in fact, we have been improving the controllers over the past years. This is something we were able to achieve last summer. This is a flight showing in real time, and here's the timer. It's a 20-second flight in real time. Maximum position error is 2 centimeters. Maximum altitude error is 2 degrees. So I would argue this is one of the best and longest hovering flight among subground flying robots. Again, demonstrating the soft robots are just capable as rigid-powered micro robots. Okay, so again, very tiny position errors and altitude errors. So now let's think about what additional functionality we can achieve in self-actuated robots, right? The first one I can think about is robustness. You can repeatedly run a wing into the obstacle, the actuator sees no damage. In fact, you can monitor the instantaneous current in the actuator to detect collisions. What you can also do is you can drive it very hard so that I can turn it on and off within 0.05 seconds. So we can do a very quick maneuver such as a somersault. And we can also force the robot to light up. So it will emit light during flight. And that's something my student Suhan Kim will present later on today in the poster session. So one of the first things we want to demonstrate is about their robust. So for the first time, we can fly 2 together. In this case, we intentionally run both into a wall just to demonstrate they can clash into something and without seeing great damages. Okay, so that's one thing that we're trying to do. But of course, we are still a long way from flying 3 or 4 together collectively. The other thing we are trying to do is take inspiration from other very famous MIT robots like the Cheetah Mini. Cheetah Mini can recover from collisions and can do a body flip. And we are asking, well, can we do similar things in our robot? So let me show you a collision recovery flight. So in this case, while the robot is flying, we gently push down on the robot, and you will see the robot is being pushed down, and then it will recover slowly to the hovering set point. Now, this is not very hard for a quadrotor. Quadrotor can do this very easily. But what's more impressive to us is now you can hit the actuator, or you can hit the actuator, or you can hit the robot wings, and the robot sees no damage, and the robot can still recover to the same hovering set point. That is very challenging for a quadrotor because you can't hit the propellers of a quadrotor when it's flying. And in the third case, I can hit the robot really hard, can't recover, but it bounces on the floor and again return back to the hovering set point. Very challenging for quadrotor, but easy for small-scale robot just because the inertial effect is much, much smaller. So for those of you who can't see the video very clearly, again, we showing you the first flight, right? Push it down gently, recovers. Showing you the second flight, we hit the actuators and wings. The robot can recover very easily. And in the third case, I hit the robot really hard, can't recover, so we bounce on the floor and eventually return back to the hovering set point. Okay. The next thing is trying to do a somersault. Again, quadrotors can do it very easily. Let's see if microscale robot can do it. And I think the advantage of the soft actuator is really can drive it really hard, turning it on and off within 4 wing beats. Okay. So in our simulation, we show this straightforward. Let me show you in experiment. So in real time, you will see everything will happen very fast. So the robot will take off and hover, and it does the flip very, very quickly. Okay, so let me now play the same video again at a much slower rate. So the robot takes off and hover around the set point for 2 seconds. Okay, and then it will accelerate backwards until it reaches a targeted point. And then it will try to do a somersault. Now, we still have issue with tracking. So once it does the somersault, we lose the tracking and it couldn't really recover. But it bounced on the floor and eventually returned back to the hovering set point. So of course, we are still working on improving the controller. If we can do a little bit of estimation, hopefully we can reduce the effect on the loss of tracking. So for those of you who can't see this clearly, again, I'm showing you a composite image showing the same thing. We take off, hover, do the somersault and return. This is a very repeatable process. We've done it 5 times straight without seeing any changes in performance. So it's not only doable, but also reliable. We can repeat it for 5 times. Finally, I just want to very quickly say that there's also additional benefit in shining out light when the robot flies. We put electroluminescent particles in the robot, and the robot can shine out light, and turns out that we can use that to do camera-based tracking. I don't have time to go into the details. What we are going to do is my student Sung-Han Kim will present in the poster session in an hour about the details of this work. Okay. So with that, let me summarize. We created a soft robots, and we show the soft robots are robust and agile. By robust, we mean the robot can recover and survive collisions. And by agile, we mean that they can do somersault. And in fact, their fastest flight speed exceeds 70 centimeters per second. Considering its small size, make it one of the fastest soft robots. Okay. And in addition, we have additional functionality such as shining out light during flight. Finally, I just want to have a brief comment about power autonomy. I think all micro robots in the long term should fly autonomously. And Farrell has shown you the state-of-the-art RoboWing this morning. If you compare RoboWing with the softline, you can see the softline is a lot worse than it first came out 3 years ago. Power density about 50% of what we have. Lift to weight ratio about 25%. Actuation voltage is about 7 times. Impossible to put batteries on board. But we are improving very quickly because we can make our own self-actuator. From last year, we improved power density to be comparable to rigid actuators. Lift to weight ratio is now 50%. Actuation voltage slightly worse. Now my group is really pushing for power autonomy. So we are doing a lot of work improving the self-actuator. As of a few months ago, we had enough time to get into the details. The power density catches up to the state-of-the-art. The lift to weight ratio catches up to the state-of-the-art. And actuation voltage now still higher, but 500 volt is already promising that a lot of the diodes and transistors can be used on board. And we're very excited to be able to do this, and we're continuing to push on improving the self-actuators. Okay, so again, very quickly on future directions, we are working on Dragonfly-like robots. We're thinking about other types of self-actuators. This is a work in collaboration with Professor Rob Shepard. We're thinking about swarm flight, and finally, we are thinking about multimodal locomotion. So with that, I want to conclude here. Just want to say that we are still very far from this long-term vision, but we are making a lot of progress very quickly. And I would argue that the next 5, 10, 20 years will be a very exciting time for people who work on micro-robotic research. Thank you.
Do you have questions? Yes, please. If possible, please use the microphone in the middle of the room.
For a very clear presentation and very awesome work. I'm from the University of Exeter, and I have one small question. I noticed that the voltage is like you want to reduce the voltage actually to control the power consumption. I see the wires are very tiny, so maybe the consumption of the wires will be very high. So how do you think in the future you're going to reduce the like to improve the material fabrication, like or to optimize the shape, anything like that? How do you continue to reduce the voltage?
Yeah, thank you for the question. I think it's very good. I didn't spend a lot of time talking about the principles of the self-actuators. You can just think about the self-actuator as a soft capacitor. So essentially, you have 2 compliant electrodes sandwich a compliant elastomer. Because it's electrostatic, it requires high voltages. So to reduce the voltage, you need to reduce the dielectric layer, which is the elastomer thickness. 2 years ago, we started with 40 microns. Last year, we pushed down to 10 microns. There's a lot of fabrication facilities in the nano facilities that can reduce the elastomer thickness to about 1 micron or less. Now, if we can do 1 micron elastomer thickness, actuation voltage will be on the order of 50 volts, right? So yes, it will take a lot of time because it requires a lot more layers, a lot more manpower. But theoretically, at least we haven't run into a trouble. We haven't run into a big limit yet. So we are quite confident that by the end of this year, we are going to reach about 300 volts. So yeah, 5 years or so, I think we can get to 100 volts or so.
Very exciting to hear this. So do you think if the layers are thinner, there will be when high voltage, there will be some problems between like touch and
yeah. So that's also a good question in the sense that when you make the layer thickness smaller, you're going to have shorting issues. And there's a phenomenon called self-clearing, which we are leveraging to get rid of the defects. But again, it's more related to material science than robotics. So I would be happy to talk to you about that offline. But I think it's a robotics conference, so we only focus on the control of the software.
Yes. Thank you. Thank you.
Okay, we do have time for another question, if there is one. Yeah, sure, please.
For your talks, I was wondering earlier you showed that you can fly two of the winged robots next to each other, and you said you're hoping to get up to 3 or 4. And I was wondering what's limiting you from doing that now? It seems like you're flying pretty fine next to each other, so why not scale up to 3 or 4 or more robots at this point?
So that's a very good question. We are actually trying to fly more in our lab. I think the limitation is not we just need the high voltage amplifiers and the processing power in our lab. It turns out that takes forever to order those high voltage amplifiers. So hopefully in 2 years we can record, fly off multiple self-actuated robots. Thank you.
So
And with that,
yeah, thank you. So this time,
yeah, let's thank our speaker.
Kevin again.
Actually, I've already selected. Maybe I'll introduce you.
Wow, that is something so small. If you try me